Hey everyone, my name is Jesse Mu, and I'm presenting our work on Emergent Communication of Generalizations. This is joint work with my advisor, Noah Goodman, at Stanford. So in this work, we tackle a classic task in multi-agent communication, which is the Lewis referential game. So this game involves a teacher agent and a student agent that need to talk about a set of objects in some common context. And the teacher is given a target image, here indicated by a red border, and needs to produce a message that, when given to the student, allows the student to identify which image the teacher was talking about. So we study this for a number of reasons. The first is to build agents that can develop communication protocols to solve tasks with each other, and then ultimately humans. And the second is to run computational simulations of language emergence. However, if we actually examine the communication protocols developed by agents in these games, we come to the conclusion that emerging a language is actually very difficult. And so there's been a wide variety of work in recent years that basically show that if you train agents on these games, they develop languages that are unintuitive, non-compositional, and generally uninterpretable. And we'd like to change that. So one of the things we do in this paper is think critically about limitations of existing reference games. And there are two main limitations that we identify. The first is that it's easy to overfit to spurious visual features in the input. And the second is that reference games are quite limited in that human language involves much more than simply pointing at objects and referring to them. For example, human language conveys abstractions, generalizations, causality, counterfactuals, and so on. And we'd like to design games that promote such abilities. To do so, in this paper, we generalize the idea of a reference game, which has a single positive target and multiple distractors, to a set reference game over sets of objects. So here there are multiple positive targets, all sharing some underlying concept of interest, in this case, red triangle. And finally, even one step further, we propose the concept game, where the inputs given to the teacher and student are separate, and it's impossible to overfit to any shared visual input. These communication games over generalizations, we will show, leads to more systematic and compositional agent languages, and additionally allow us to test for the emergence of richer behavior in our agents, such as generics, quantifiers, logic, and more. And finally, we propose a tool called Acre for discovering logical compositional structure in emergent languages. We're going to use two datasets in this work. The first is the shape world dataset, which allows us to test for abstract concepts involving multiple images and various combinations of shape and color features, as well as a more realistic birds dataset, where the concepts are defined by species of birds and have corresponding concepts defined as logical conjunctions of the relevant bird features. Our teacher and student models are standard neural architectures for a task like this. So the teacher is a conditional grounded language model, which takes as input averaged prototypical representations of the positive targets and the negative distractors in the game. And our student takes in a teacher message and an image and makes predictions for each image as to whether or not it belongs to the concept identified by the teacher. If we train models on this task, we can see that the models perform quite well. The reference game tasks are obviously the easiest, and so models get the highest accuracy on those tasks, and the accuracy is somewhat lower for set reference and concept games, indicating that the task is harder. But ultimately, we're interested in evaluating the compositionality of the learned languages. What we're left with after training is a dataset of concepts and corresponding messages produced for each concept. And we would like to evaluate the claim of whether or not set reference and concept games lead to more systematic and compositional agent languages. So there's a variety of ways that we actually measure this in the paper, but I'll go over one of them, which is topographic similarity, which tries to capture the notion that similar concepts should be given similar messages, and this is generally true of human languages. To do so, we're going to first define a distance function between concepts, d of c, which we'll define as edit distance, and a distance function between messages, which we'll also define as edit distance. And then given these distance functions, we're going to compute the rank correlation between pairwise distances of c and m. So here's an example of a language with low topographic similarity and a language with high topographic similarity. And what we see is that throughout training, the set reference and concept game agents show greatly increased systematicity measures across both datasets, across both seen and unseen concepts. And we can verify this by actually looking at the distribution of messages produced for games of a certain concept. For example, for red and triangle, here is a distribution of messages generated by a concept teacher for all games that encode this concept. And so this is a nested pie chart where each color corresponds to a unique token, and you should read from the inside out. So what this is saying is that for concept agents, messages generated for the concept red and triangle overwhelmingly begin with the token D followed by 4 E's, or less commonly E followed by D followed by 3 E's. The language for the set reference game agents is a bit more varied, but this pales in comparison to the language generated for red triangles for agents trained in reference games. And you can see here how reference game agents use a bewildering variety of messages to refer to different red triangles, and it's really difficult to see any correlation between the logical concept and the message generated by the reference game agents. And this is illustrated in the differing entropies of the distributions that you can see at the bottom here. We have a lot more examples of this in the paper, so please take a look. But finally, as I mentioned, one advantage of these set reference games is that they allow us to test for concepts that apply across multiple inputs. So we not only have distributions of messages for the concept red triangle, but also messages for the concepts red and triangle. One thing that set reference and concept games should let us do then is ask to what degree compositionality is actually occurring in these languages. So if we can squint at the distribution of messages for red and triangle, are they actually meaningfully composing together the tokens they use to refer to red and triangle separately? In other words, is there a lexical operator in the language that operates akin to the English word and, where if you give it two messages, such as red and triangle, and then you and them together, the corresponding message you get out means the conjunction of its arguments. And crucially, like the English operator and, this operator must apply across the entire agent language for arbitrary combinations of concepts. So we're going to try to actually learn an operator in the agent language. And to do so, we propose our procedure, which we call Approximate Compositional Reconstruction, or ACRE. The basic idea is to first train approximations to the primitive concept in our data set. So singleton concepts like red and triangle, we're going to train an unconditional language model to mimic the distribution of messages for these concepts. And then given these models, we're now going to try to search for a composition operation which reliably composes these messages together. So as an example, if we want to train our AND model, and we know that the agent produced the message BCA for red and triangle, we're going to train a generic sequence-to-sequence model to produce this message from samples from the constituent primitive language models. And notice that because we formulate this as a sequence-to-sequence learning problem, we make few restrictions on the format of this composition operator. In particular, we don't enforce that there's a specific token denoting AND, or that the arguments are copied verbatim in the output. These constraints are generally true of human languages, but there's no reason to expect them in our agent languages. We can learn these operators across the entire data set, including not and or operations. Now that we have this approximate reconstruction, the way we're going to evaluate it is we're going to take a student, which ordinarily takes in teacher language and makes a prediction, and at test time, we're going to replace the messages generated by the teacher with messages generated from our compositional reconstruction. And if the messages provided by ACRE induce the right behavior in the student, we can say that ACRE has, to some degree, learned the compositional semantics of the language. So here are results. As an upper bound, we're going to compare to the accuracy obtained by a student when given the true teacher language. And as a baseline, this is both blue score with the teacher language as well as student accuracy if we give the student a random message sampled from the vocabulary, as well as what it looks like at the bottom here. Here's a stronger baseline where, given a concept like yellow and triangle, we're going to sample messages from the closest concepts to this concept in edit distance space, and this is the blue and accuracy scores it achieves. And finally, here is ACRE, our compositional reconstruction. So you can see that ACRE certainly outperforms both baselines in terms of lexical overlap with the true language as measured by blue and student accuracy on the actual task itself, although it's still a ways away from teacher accuracy. And this remaining gap could be due to two factors. One is lack of compositionality in the actual agent language, and two could be the failure of Acre to generalize compositionally. So to summarize, these reference games over sets really serve to regularize the languages that are produced by agents, which tries to capture the human intuition that human languages are biased towards the communication of generalizations. And furthermore, these games allow us to evaluate the emergence of what is really a vast variety of linguistic abilities that humans develop that are just not testable with standard reference games. And so follow-up work really tries to look at these two properties more closely. The first is that Acre has shown that compositional operations in agent languages are learnable but aren't particularly intuitive. And so some follow-up work should be done to encourage more transparent composition in these emergent languages. And the second is thinking about how we can adapt this paradigm to encourage development of richer linguistic phenomena such as spatial relations, quantification, or even instructions and causality in embodied environments. I think there's a lot of exciting work to be done here, and the core argument of this paper is to really begin to consider task difficulty when setting up studies for emergent communication. Thanks for listening, and I'm happy to take questions in the poster session.